A just before it hits block B. What did we cover 2 chapters ago? Energy, right? So when something, if you see something fall, or if you see something's moving, or if you see a spring compressed or a rubber band stretched, you should think of energy every time. Like, oh, that rock could fall, energy. Oh, look, that spring is getting stretched, energy. So then I can say mechanical energy initial equals mechanical energy final. E, what's the energy in the squared? M's cancel, and we get V is the square root of 2GH. Yeah, question. Good. Now we can say inelastic or elastic. What is true about momentum, Joan? Momentum is conserved. Then I can say Pi equals Pf. So you see this problem is just a bunch of conservation stuff. And who was moving in the beginning? Yeah, well actually let's go ahead and do it fully, right? There's PA plus PB equals PA plus B, right? Because they stick together. PB is 0, right? Because it's not moving at the moment of collision. So we get M, MA, well, I'm just going to say M because they're times V. So V and these M's will cancel, and I get is equal to VA over 2, which is equal to the square root of 2GR over 2. Good, I was recording it. Hopefully you remember from the definitions that you have in your book, an inelastic collision conserves what, David? All collisions everywhere, anytime, any place, conserve what? No, not it. Mr. Mendez. Momentum. All collisions conserve momentum. All right, but inelastic collisions do not conserve energy. So what I get is there is a change in kinetic energy, or KE final minus KE initial. And I think once I write that, you can do this, right? It's not that crazy. And so you say KE final is going to be 1/2 times 2m times, that's going to be like v squared, minus, and what was moving before the collision? Yeah, just m, right, at VA, so it's 1/2 m VA squared. And so when I do this, I don't know, that's going to cancel with that, and I'm going to get m times, and this is v, so I'm going to get m times, well, yeah, let me go ahead and 2GR over 2 squared minus m over 2 times square root of 2GR squared, right? Do you see what I did there? I just plugged them in. This is V, plugged it in. That's VA, plugged it in. And when we do that, I get my M here, and then this becomes GR over 2, I think, and then minus MGR, which gives me negative MGR over 2. That's how much energy we'll lose. Everyone here has had chemistry, right? Has anyone here not had chemistry? Anyone not had chemistry? Oh, cool. So that was no big deal. You should be able to do that. For D, you would say delta KE is equal to Q, or whatever, like the amount of heat gained. So it's going to be MGR over 2 is equal to 2MC delta T. So delta T, the M's are going to cancel, obviously. Delta T is going to be equal to GR over, oh, yeah, well, that's with respect to, that's the amount of change in kinetic energy. So the absolute value of this is going to become heat, right? So I guess I should put this. Actually, I need the last one. To the block. Sal, what happens? Yeah. Yeah, it's just moving that way. What happens to the block? Does it change in any way? David, what do you think? There you go. And how does it change? Sorry? You said the velocity changes because of friction. Yes, very good. Does everyone see that? When it slides from Y to P, it will be going slower than it was when it started at Y. And remember, what was the velocity at Y? It was this. Yes? Does this make sense? So at P, it's going to have some lower velocity. And we know that what changed it? David said it was friction. So the work done by friction is going to be what causes another change in heat. And that's mu times 2m. Oops. What's supposed to be E? What? What was this E? Oh, part E. Oh, sorry. Sorry. There you go. Sorry about that. Right? Because the amount of energy that it's going to lose, which is going to become more heat, is that. And that's all they ask, is what is the additional energy lost? And there we go. That's our problem.